Lakshmi Prasanna, Assistant Professor, Department of ECE, Institute of Aeronautical Engineering. In this session, we will discuss about 8251 USART architecture. So, before going to the architecture of 8251, first we will see what are the features of 8251 USART. So, USART stands for Universal Synchronous Asynchronous Receiver Transmitter. SIP 8251 USART is developed by Intel and it is compatible with different microprocessors like 8085, 8086 and 8080 and 8088. So for any microprocessor, we can use this 8251 USART. Okay. So 8251 stands for Universal Synchronous Asynchronous Receiver Transmitter. So what is the need of using this USART 8251 IC means? This USART IC is going to convert parallel data to serial data and serial data to parallel data. That is why we will say this 8251 USART acts as a mediator between microprocessor and peripheral devices to convert the serial data into parallel form and parallel data to serial data. Now, so generally here the peripheral devices, that is IO devices, will take or will generate output which is in the form of serial manner. But here the microprocessor will take the data which is in the form of parallel and it is going to do some operations on that parallel data and again it is going to produce the output which is in the form of parallel. And that parallel data will be given to the peripheral devices. But here the peripheral devices will take only serial data as the input. That is why in these cases, in order to convert serial data to parallel data and parallel data to serial data, we should have this 8251 USART as a mediator between these IO devices and microprocessor. So it takes data serially from the peripheral devices and converts it into the parallel data. And after converting the data into the parallel form, it transmits to the CPU. So here CPU is microprocessor and it receives the parallel data from the microprocessor and again it is going to convert it into the serial form. So here it means USART IC, which is called 8251A. And after converting the data into the serial form, then it is going to transmit the data into the outside world, that is output device, which we will call as a peripheral device. Now, so here this 8251 IC is available in 28-pin dual inline package. So here it is having 28 pins. All the 28 pins will be arranged in the dual inline package. So dual inline package means first at one side 14 pins will be there. At the other end remaining 14 pins will be available. So this is what arranging the pins in the dual inline package format. And so here all the inputs and outputs are TTL compatible. So here TTL compatible means transistor logic. So transistor logic means here the voltage levels will be represented in the form of 0 volts and 5 volts. Generally here the data will be transmitted in the form of binary. Either it may be 0 or 1. So in order to transfer 0, it will be indicated with the help of 0 volts and in order to represent the binary data 1, it will be represented with the help of 5 volts. So this is what representing in the form of TTL, transistor logic. And this 8251 USART is able to detect parity, overrun and framing errors. So how it is going to detect this parity, overrun and framing errors means, because in this 8251 we have status word register. it is an 8-bit register. So among that 8 bits, 3 bits are related for detecting the errors like parity error, overrun error and framing error. So using the 3 bits, these errors can be detected. So all these are the features of 8251 USART. And next, coming to the block diagram of 8251. So this is the block diagram of 8251. So totally it consists of 5 sections. So here, this is one section which is called data bus buffer. So to this data bus buffer block, here we can observe there is a bidirectional data bus D0 to D7. There are 8 data lines. It is bidirectional. So through these 8-bit bidirectional data bus, this USART is going to communicate with 8086 microprocessor. So it is going to send the information like status words and control words to 8086 microprocessor. And the second section is here read-write control logic. So this is the main block which is going to control all the operations of 8251 USART. So to this block here, all the control signals like write, read, reset, clock, C by D bar and this is chip select. So all these are the control signals that are connected to this read-write control logic. So this block will control all the operations of 8251 USART. And next block is here modem control. So this modem control is the block which will be converting, which is used for conversion. So this modem is the block which will be converting the analog signals to digital and digital signals to analog. So here this is the modem which will be communicating this computer to internet by using the telephone lines. So this is the main function of this modem control. So here all the signals that are related to perform this conversion and to connect this computer to the internet by using the communication network, that is telephone line. We have the signals like DSR, data set ready, DTR, data terminal ready, and CTS, clear to send, and RTS, request to send. So using these 4 signals only, DTE and DCE devices will be communicating. So here DTE represents data terminal equipment and DCE represents data communication equipment. So these are the 3 blocks. And another block of this 8251 USART is, so here we will have this transmit buffer and transmit control. So these 2 blocks are called, totally these 2 blocks comes under transmitter section. So this comes under transmitter section. So in this transmitter section, we have this transmit buffer block and this transmit control block. Okay. So here the signals related to the transmitter section are TXD. So TXD represents transmit data and TXRDY, that is transmitter ready, TXEMPTY, transmitter empty, and TXC, transmitter clock. So these are the 2 blocks and signals. So using these signals, the data will be transmitted from the transmitter section. And from the transmitter section, whatever the data we are transmitting, it will be in the form of serial manner. That means here transmitter section will take the parallel data as input and it is going to produce the output as the serial data, and that serial data will be transmitted through this transmitter section. And next block, so this is the 4th section, and the next block here we have receive buffer and receive control. So these 2 blocks comes under receiver section. So this is the 5th block. These 2 blocks comes under receiver section. So here the receiver related signals like RxD, that is receive data, RXRDY, receiver ready, and RXC, receiver clock, and this is sync detect, break detect. So by using all these signals and the blocks like receive buffer and receive control, this receiver section is going to receive the data, and the received data will be in the form of serial manner, and that serial data will be converted into parallel data after received by the receiver. So these are the 5 important sections that are available in the block diagram of 8251 USART. Now, so coming to the detailed discussion about each block of 8251 architecture. So here totally it consists of 5 sections. What are the 5 sections? Data bus buffer, read-write control logic, modem control, transmitter section, and receiver section. So we will discuss about all these 5 sections in detail. So the first section is here data bus buffer. So this data bus buffer block, we have D0 to D7 bidirectional data bus. So using this bidirectional data bus only, this 8251 is communicating with 8086 microprocessor. So using this D0 to D7 bidirectional data lines, this 8251 and 8086 will be communicating. The data will be transmitted between 8251 and 8086. So what type of information will be transmitted between these two means the information like control words, status words, and data. So all these can be sent from processor to 8251 and 8251 to processor, that is USART to processor. That is what about data bus buffer section. And next section, second one, here read-write control logic. So this is the main block which controls all the operations of 8251. So this is called the control block. So it is the control block for overall device, and it controls overall working by selecting the operation to be done. Here the operation what has to be done will be selected based on the control signals that are connected to this read-write control logic block. So here we have the control signals connected to this block like chip select, C by D bar, R D bar, and WR bar. So based on these 4 signals only, the control of 8251 will be done. 8251 control will be done. So here using these 4 signals, if it is 1, CS bar 1 and the remaining all signals are don't care, it represents invalid operation. Nothing will be done. And if the signals CS bar 0, C by D bar is 0 and RD bar 0 and WR bar is 1, data will be transmitted. So just we have seen the 8086 microprocessor and 8251 USART will be communicating with each other, and the data that will be transmitted, either it may be control signals, data or status information. Okay. So if it is this combination, only the data will be transmitted from 8251 to CPU. That is from 8251 to 8086 microprocessor. And the next combination is 0010. Here the data will be transmitted. So here in this case the CPU is going to send the information to 8251. And 0101, the information like status word will be transmitted from 8251 to CPU. And if the combination is 0110, the control word will be transmitted from CPU to 8251. So in this way, the operation selection will be done. So the operation selection mainly depends upon the control signals which are connected to that particular block. So that is what about the read-write control logic block. And next one is modem control. So here modem represents modulator and demodulator. So it is going to convert analog signal to digital and digital signal to analog. So this is the hardware unit which will be acting as a switch in order to connect computer to the internet by using the telephone lines. So here a device, that is modem, is a device that converts analog signal to digital signal and digital signal to analog signal. And this modem is going to connect these computers to internet by using the telephone lines. And so in order to do all such operation, here there are some active low pins. So here what are the pins that performs all these operations means? The first one is DSR. So here DSR represents data set ready. So DSR represents data set ready. And the next signal is DTR. So DTR represents data terminal ready. And next one is RTS. So RTS represents request to send. And next is CTS. So CTS represents clear to send. So all these are the four signals that plays the major role while this DTE and DCE devices are communicating. So for example, if you consider here, this is a DTE device, that is data terminal equipment. So here data terminal equipment can be CPU. And here if you consider DCE, so DCE represents here data communication equipment. So the data communication equipment here can be modem. So in between these two, these four signals plays the major role to perform such operation. That means first the CPU is going to send a signal called DTR. Okay. And in accordance to that, after receiving this DTR signal, the modem is going to send a signal called DSR. So DSR represents data set ready. So when this DTR is sent from this CPU to the modem, it indicates that this DTE is turned on and it is ready for communication. So this is the meaning of this DTR signal when it is sent from CPU to the modem. When this modem receives that, it is going to send the DSR. So the purpose of this DSR signal is it indicates connection to network. Okay. So when these two signals are done, it indicates that these two signals are connected and next they can communicate with each other. So after these two signals, these two are one pair of handshaking signals, and another signal after this DSR has been received by CPU, it is going to send a signal called request to send. Okay. So this RTS signal, it indicates it has a byte to send. That means the CPU is having information to send to the modem. After the modem receives this RTS signal, it is going to send a signal called CTS. So here CTS represents clear to send. So when the CTS signal is sent from modem to the CPU, it indicates that the buffer space is empty and it is ready to receive the data what the CPU is transmitting. So here when the CTS signal is asserted, it indicates buffer space is available. Buffer space is available for incoming data. buffer space is available for incoming data. Okay. So with the help of these two signals, the communication will be performed. And so we will discuss this DSR, DTR, which one is the input terminal, which is the output terminal now. So these are the active low pins. Okay. So DSR represents data set ready. This is the input signal. And next one is DTR, data terminal ready. This is the output signal. And RTS represents request to send. And this is the output signal which is used to set the status of RTS. And next one is CTS. CTS represents clear to send. So it is an input signal which controls the data to the transmitter circuit. And so that is what about the modem and the signals that are connected to the modem. And next section is transmitter section. So in the transmitter section, we have seen the block transmitter buffer is there and transmitter control is also there. So here generally, if you consider this is a transmitter section, to this transmitter section, we are going to receive the parallel data as input to the transmitter, and this transmitter, it is going to convert into serial data, and that serial data will be sent to the communication channel. And so this transmitter section, it accepts parallel data from the microprocessor and converts them into serial data. And so this is the transmitter section. So here it consists of different blocks like transmitter buffer and output register. So here whatever the data here we are getting, it will be in the form of parallel manner, and this parallel data will be first kept in this transmitter buffer block, and this parallel data will be converted into serial data. Okay, so here this transmit control block will have all the control signals. So these control signals will be connected to the output register block and also transmitter buffer block. So this transmit control block will control this transmitter buffer and output register. So this parallel data will be first kept in the transmitter buffer and then it will be sent to the output register. So through this TXD signal, the serial data will be transmitted into the communication channel. So here we have this TXD, TXRDY, transmitter ready, and TXE, transmitter empty, and TXC, transmitter clock. And so in the transmitter section, we have this transmit buffer block. So what is the function of this transmit buffer block means? This block is used for parallel to serial conversion, that receives a parallel byte for the conversion into serial signal, and further it transmits into the communication channel. So finally the serial data will be communicated through the channel through TXD signal. So here this is the TXD signal. So TXD represents transmit data, and this is the output signal for that transmitter section block. Using this signal only, the data will be transmitted. So if the value is 1, it means the data is transmitted. Now, so next block is transmit control. In the same transmitter section, we have transmitter buffer and transmit control. So here, this transmit control block is used to control the data transmission with the help of the following pins. That means to the transmit control, we have seen in the block diagram, 3 signals are connected. That is transmitter ready, transmitter clock, and transmitter empty. So here are the 3 signals. TXRDY represents transmitter ready. So it indicates that if this TXRDY signal is enabled, it indicates that the transmitter is ready to transmit the data or character. And the next signal connected to this transmit control block is TXEMPTY. So TXEMPTY represents transmitter empty. So this signal is an output signal which indicates that TXEMTY pin has transmitted all the data characters and transmitter is empty now. So after sending all the data that is there in the transmitter section, then automatically this TXEMTY signal will be enabled. So if the TXEMPTY signal is enabled, it indicates that the complete data has transmitted and there is no information present in the transmitter. And the next signal is TXC. So TXC represents here transmitter clock. It is an active low input pin which controls the data transmission rate of the transmitted data. So that is what about the transmitter section. Next here, coming to the receiver section. Here the receiver is going to receive the information whatever has been transmitted by the transmitter. So the transmitter has transmitted the serial data. So that is why here the receiver is going to receive that serial data. The receiver is going to receive that serial data and that serial data will be converted into parallel form and that parallel information will be given to the microprocessor. So this is what will happen at this receiver section. So this receiver section accepts the serial data on the RxD pin and then it converts into parallel form. And so this is the receiver section block diagram. So through this RxD signal, this receiver is going to receive the data. And this received data, it will be the serial data. And this serial data will be converted into parallel data. And this parallel data will be given to the CPU, that is microprocessor. So here, whatever the serial data that has been came here, it will be first kept in this input register. And here, after performing the conversion, that converted data will be taken by this receiver buffer and it is going to give to the CPU, which is in the form of parallel form. And here we have this receive control. This receive control block will control the two blocks. So this input buffer, that is input register and the receive buffer, both these blocks will be controlled by these three control signals. Here this is RxRDY, receiver ready, sync detect, break detect, and this is RxC. So these are the three signals that are connected to this receiver section. Now we will discuss about this receiver buffer block and receive control block that are present in this receiver section. And here this is receive buffer. So this receive buffer block will accept serial data. Then it is going to convert the serial input into the parallel format. Now, so to the receiver section, through which signal this receiver is going to receive means, by using the signal called RxD, it is going to receive and it is clocked on the rising edge of the RxC, that is receiver clock. And the signals that are connected to this receiver buffer is only one, that is RxD. So RxD represents here receiver data or receive data. So this is an input signal which receives the data. That is what about receiver buffer. And next section is here receive control. So this block will control the receiving data. And to this receiver control section, we have different signals like RX, RDY. So here RX, RDY represents receiver ready. So this receiver ready, it is an input signal which indicates that it is ready to receive the data. So if this RX, RDY signal is enabled, it indicates it is ready to receive the data. So it is having the buffer space. So it is able to receive the new data and keep in the buffer, receiver buffer. And next signal is RXC. So here RXC represents receiver clock. So this is an active low input signal which controls the data transmission rate of the received data. And next signal is here sync detect and break detect. So this is an input or output terminal. So it is a bidirectional pin and it is used in the synchronous mode as sync detect. If this 8251 is operating in the asynchronous mode, it will be acting as a break detect. Now, so that is what about the block diagram of 8251 USART. Now, coming to the control words that are available in this 8251 USART, there are two types of control words. So here there are two types of control words. One is mode instruction and another one is command instruction. So these are the two types of control words available in 8251 USART. Again, this mode instruction is having bit configuration of mode instruction in the asynchronous mode and bit configuration of mode instruction in the synchronous mode. So generally this mode instruction is used for setting the function of this 8251 USART, whereas this command instruction is used for setting the operation of 8251 USART. Now we will discuss about this mode instruction in both asynchronous and synchronous mode, and command instruction, how that particular instruction will be. So these two comes under control words, and along with this control words we will also discuss about status words. So first we will see about this mode instruction format. So this is mode instruction format. This format is used to set the function of 8251. So how it is used to set the function of 8251 means, because it is an 8-bit register and here it has the 8 bits like deciding the stop bit length, and using that format we can also say the character length and parity bit, whether it is even parity or odd parity, and baud rate factor can be set, and internal or external synchronization, number of synchronous characters. So all these parameters can be decided by this mode instruction format. So again in the mode instruction format we have asynchronous and synchronous. So first we will discuss about here asynchronous. So when the data, that is serial data, that is being transmitted in the form of asynchronous mode, along with the original data we are going to include the start bit and stop bits. Okay. So here this mode instruction format asynchronous, so it is an 8-bit format having the bits from D0 to D7. So here this D0 and D1 bits, that is B1 and B2. Okay. So these two bits together will decide the baud rate factor. So if these two bits are 0, 0, it will be operating in the synchronous mode, not asynchronous mode. If it is 0, 1, baud rate factor will be multiplied with 1. And if it is 1, 0, baud rate factor will be multiplied with 16. If it is 1, 1, baud rate factor will be multiplied with 64. So these two bits decides the baud rate factor. So baud rate means the number of times the signal in the communication channel changes. And The next two bits are D2 and D3, which represents here L1 and L2. So using these two bits, the character length can be decided. So the character length may be either 5 bits, 6 bits. So how to fix this character length means, if these two bits are 0, 0, the character length is only 5 bits. If this is 0, 1, the character length is 6 bit. If it is 1, 0, character length is 7 bit. If it is 1, 1, character length is 8 bits. So these two bits decides the character length. And next bit D4. So D4 here represents PEN. Okay. So here PEN represents parity enable. So this signal, it represents parity enable. So this is about asynchronous, talking about this D4 bit. Okay. So generally we have to send the parity bit in order to detect the errors that are present at the receiver edge. So in order to do that, we have to use this PEN signal and this D5 bit EP. So here this EP represents, so generally these two are called parity control signals. Okay. So this EP represents enable parity. Okay. So if these two signals are 0, 0, parity will be disabled. If it is 0, 1, odd parity will be enabled. If it is 1, 0, parity will be disabled. If it is 1, 1, even parity will be enabled. And the next two bits are D6 and D7. This D6 and D7 bits represent the stop bit length. So here in the asynchronous mode only, we will have this stop bit length. Why? Because in the synchronous mode, we will not include any start bit and stop bit. So start bit and stop bit will be included only in the asynchronous communication. So this S1 and S2 bits represents the stop bit length. So if it is 0, 0, the combination is invalid. If it is 0, 1, only one stop bit will be included. If it is 1, 0, 1.5 stop bits will be included. If it is 1, 1, 2 stop bits will be included. So this is what about the 8-bit register format of bit configuration of mode instruction in asynchronous mode. For synchronous mode also, we will have approximately the same format, but these bits will be changing in the synchronous bit format. So if you observe here, this is the bit configuration of mode instruction in synchronous mode. So here, since this is synchronous mode, if you observe here, we will not find any information or bits related to stop bit. Why? Because in the synchronous, we will not include any stop bits, whereas the remaining bits will be same. So this is also an 8-bit format. Here the first two bits D0 and D1, they will be fixed to 0, 0. And coming to here, this D2 and D3 bits, these two bits represents the character length. So if these two bits are 0, the character length will be 5 bits. If it is 0, 1, character length is 6 bit. If it is 1, 0, character length will be 7 bits. If it is 1, 1, character length will be 8 bits. And next bit is D4 and D5. So D4, this is PEN, which represents parity enable. And this is EP, enable parity. So these two bits represents the information related to parity. So during communication here, we have to include the parity bits, because in order to know whether it is even parity or odd parity, we have to include. In order to know whether there is any error or correct data is received by the receiver or not. So in order to have parity, if these two bits D4 and D5 are 0, 0, parity will be disabled. If it is 0, 1, it represents odd parity. If it is 1 0, parity will be disabled. If it is 1 1, even parity. And this D6 signal, so here this is the D6 bit which is represented as ESD. So it represents external sync detect. Okay. So external sync detect means it represents sync mode of operation. Okay. So in order to operate in the synchronous mode, so if this D6 bit is fixed to 0, it represents internal synchronization. If the D6 bit is fixed to 1, it represents external synchronization. And the next bit is here D7. So D7 is here SCS. So here SCS. It represents single character sync. Okay. So here this bit represents the number of synchronous characters. If it is 0, 2 characters will be included. If it is 1, only 1 character will be there. So this is the register format of bit configuration of mode instruction in the synchronous mode. Again, in this control words, along with this mode instruction format, we have command instruction format also. So this command instruction format is used for setting the operation. So here this command instruction is used for setting the operation of 8251. That means here this 8251, this command instruction is a 8-bit register having 8 bits which are used for setting the operation. So the bits are related to transmit, whether to make the transmitter enable or disable, whether to make the receiver enable or disable. Okay, so information like DTR, RTS, and resetting of error flag, sending to break characters, and internal resetting. So all these parameters can be programmed by changing the bits that are present in the command instruction of 8251 USART. It is an 8-bit register. Now, so this is what the bit configuration of command instruction. So this is the 8-bit register format. So in this here D0 represents TXEN. So TXEN means transmitter enable. So if the D0 bit is made 1, transmitter will get enable. If it is 0, transmitter will be disabled. And next D1 bit is DTR. So DTR represents data terminal ready, and it is active low signal. So if that bit is made 1, it indicates DTR bar is equal to 0, that is data terminal ready is enabled. And if it is 0, DTR bar is equal to 1, disabled. And here D2 bit represents RXE. So RXE means receiver empty. If that bit is fixed to 1, it means receiver is enabled. If it is fixed to 0, receiver will be disabled. So here this RXE represents receiver enable. And SBRK here, sent break character. So if that bit is 1, sent break character. If it is 0, the normal operation will be performed. And here this ER represents error. So in order to detect the error or not, this bit will be used. So if this ER bit is 1, reset the error flag. If this is 0, the normal operation. And next D5 bit is RTS. So RTS represents here request to send. So this is an active low signal. If that bit is 1, this RTS bar is equal to 0. That means request to send operation will be done. If it is 0, this RTS bar will be 1. That means it will be disabled. And next signal is D6. And here D6 represents IR. So IR is here internal reset. So if the signal is bit is 1, internally reset. 8251 will get internally reset. And if it is 0, the normal operation will be performed. And here D7 bit is EH. Here this EH represents error hunt mode. So this is one of the mode for finding the errors. If that bit is 1, it will be operating in the error hunt mode. If it is 0, normal operation. This is the bit configuration of command instruction. So all these formats, whatever we have seen up to now, those comes under the control words. So here 8251 will send the control words or status words to 8086. So all these are the control words. Next, coming to here, the status word register. Here this status word register is used to set the internal status of 8251 by reading a status word. So here the bit configuration of status word is given. So it is also an 8-bit register having the bits from D0 to D7. So here this D0 bit represents TXRDY. So TXRDY represents transmitter ready. So when the signal is enabled, it represents transmitter is ready to transmit the data. And next D1 represents RXRDY. So RXRDY represents receiver ready. So here receiver ready, if the signal is enabled, that means if this D1 bit is 1, it represents that the receiver is ready to receive the data. That means it is having the buffer space, so it is able to receive the data. And D2 bit is TXEMPTY. It represents transmitter empty. So when the signal is enabled, it represents that the transmitter is empty and there is no more data present at the transmitter to transmit. And so this D3 bit represents PE. So PE here is parity error. So in order to detect the parity error, that means if you are transmitting the even parity at the transmitter side, at the receiver side, whatever the data is received, if it is having the odd parity, then it is called a parity error. So in order to detect such type of error, this D3 bit should be made as 1. And D4 bit is OE. So OE represents here overrun. Okay. So in order to detect this overrun error, we have to make this bit as 1. So here what is meant by this overrun error means, if first character is not received before the second character is received, then we will say that it is having overrun error. And D5 bit is FE. FE represents framing error. Okay. So here in the features we have studied that this 8251 USART is able to detect parity error, overrun error and framing error. So that is what, by using the status word register, these 3 bits, it is able to find such errors. And the next D6 bit is here SYN-DET, that is sync detect and break detect. So here the sync detect and break detect, generally same terminal, that means if it is operating in the synchronous mode, this sync detector will be activated. If 8251 is operating in the asynchronous mode, this break detector will be activated. And D7 signal is DSR. So this DSR represents data set ready. So here this is the D7 bit. This is active low signal. When this bit is 1, it indicates the data set ready is enabled. If it is 0, the data set ready will be disabled. So this is what about the status word register format of 8251 USART. So this is the block diagram explanation of 8251 USART. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.